afternoon to everybody. I'm Gilles Trombettoni, and I'm going to present a combinatorial solver designed by these co-authors based on interval techniques to solve the so-called differential-algebraic CSP. I'm first focusing on the summary of the context and the contribution of this work. The goal of this work is to propose a solver for the very generic problem called here DA-CSP, where a network has two types of variables. First, continuous real variables, whose domain are intervals, and also functional variables, or trajectory, whose values are functions, in orange on the figure here, and the domains are tubes, illustrated by the gray parts of the figure. These variables allow one to describe, for instance, the trajectory of a mobile robot, but are widespread also in physics, biology, and so on. Different possible constraints can be defined in a DA-CSP network: standard numerical constraints, equations or inequalities, and also differential constraints like OD. The OD are the most common differential constraints, where the derivative of the trajectory of time t depends on the value of x at the same time t, but also integro-differential equation, where the derivative of x depends also on the values of x before t, because of the integral here. And we can also have mixed DA constraints, for instance, the evaluation or observation constraint here, where x and v are trajectories, and tk and y are real numbers, and this constraint just states that the trajectory must pass through the value y at time tk. The contribution of this work first lies in the model itself. It's generic, it can model numerous real-life problems, and is in a sense simple, especially because the trajectories are considered as true variables of the CSP networks. And the main contribution is a combinatorial solver built upon C++ libraries for intervals and tubes. And an original features of this solver is a tree-search strategy, where choice points can be performed by splitting a tube in two subtubes. And this allows the DA-CSP solver to compute several solutions, or to better approximate each solution. And the other ingredients are dynamic contractors. A contractor is a filtering procedure close to a propagator for finite domain CSP. And we propose a homemade differential contractors and an efficient ODO contractor that wraps the state-of-the-art V-node solver. As an example of what kind of system our generic solver can handle, we show a system with an integro-differential equation, not an ODE here, and instead of a usual initial condition, this so-called boundary value problem must satisfy a constraint between the initial time 0 and the final time 1. And as you can see in the figure, this exact determinist solver can approximate the two trajectories by small tubes. This slide ends the summary of this work. In the second part of the talk, let's present a background about intervals, dynamical systems, and tubes. First, what are intervals and boxes? An interval is simply a set of real numbers bounded by floating point numbers. A box is a set of intervals, a Cartesian product of several intervals. The width of a box, or size or diameter, is the maximum size over all the dimension. Several operations can be performed on intervals. First, it's possible to extend the real functions to intervals. The natural extension consists in using interval arithmetic for all basic mathematical operations. On this example, without detailing the natural evaluation Fn, into brackets, of the interval 0, 1 computes 0, 2. This means that for any value between 0 and 1, the image by f gives a value necessarily comprised between 0 and 2. A major issue is that in general, the result is not optimally sharp. Here, this value 0 cannot be the image by f of any value of x between 0 and 1. In this case, it's due to the multiple occurrence of x in the expression of f. For this reason, and because the function handled can be nonlinear, interval methods for solving systems of static equations are combinatorial. They follow a branch and filter principle, where the branching is called box bisection and the filtering on the interval bounds is called contractions. Let's illustrate the branch and contract principle on a system of two equations, one in red and one in blue, where the domain of x1 appears in abscissa and the domain of x2 appears in ordinates. By applying a contraction algorithm like HC4 revise on the red equation, we can contract the initial domain to the white box. Then the same algorithm contracts the box again using the blue equation and again with the red equation. We then proceed to a choice point by bisecting the interval of x1, which produces two subboxes. The same propagation contracts again the box in the left branch, and another contraction algorithm can quickly converge on a small box, including the unique solution, in green here. The same process applied to the right box compute the second solution. Overall, starting with an initial box, the branch and contract process was able to compute two small boxes in green, accurately approximating the two solutions. Interval method can also be applied to dynamical systems. Let's first record the two differential constraints used in our experiments, well-known ODEs, and integro-diff equation, where the derivative of the function depends on the state at different times between t0 and t. These differential equations allow the definition of several dynamical problems. First, the well-known initial value problem defined by an ODE and an initial condition. A generalization is the interval IVP, where the initial condition is uncertain, comprised in an interval, and the solution is a thick trajectory, as we will see further. The third problem is the boundary value problem, where the initial condition is replaced by a set of constraints, generally on the bounds, like the last constraint here, between x at time 0 and x at time 1. As already seen in the first part, the solution of a dynamical system is a trajectory, in orange here, and the domain is a tube, in gray here. Interval can be used to approximate tubes by a sequence of contiguous slices. A slice is a box, vertically, that encloses the trajectory during a temporal domain interval horizontally. For operational reasons, a given slice is represented by an envelope and gates, in bold here, in which the trajectory must pass. In this part, we are going to present our DA-CSP solver. This solver works in three phases: first, slicing; second, the backtracking step; and third, solutions merge. Let's first define what is a slicing operation. It consists in splitting a slice at the middle time, take key here, which creates an additional slice in the tubes. This interval sampling operation is useful to limit the wrapping effect, and thus to improve the interval numerical method used to compute solutions of dynamical systems. The slicing phase interleaves contractions and slices splitting until all slices are sufficiently small, I mean in the x dimensions, or until a maximum number of slices is reached. The best slicing policy splits several slices simultaneously between two contraction steps. For instance, we split half of the slices and the largest one. When the slicing phase ends, the solver builds a search tree in depth first order. This search interleaves tubes bisection and contraction. For performing a tube bisection, we first select an instant and then branch on the corresponding gates where the trajectory must pass. In the example, the tube bisection enabled to discriminate the red trajectory that will pass through the upper subtubes and the blue trajectory that will pass through the lower subtube. As seen above, both tube slicing and tree search phases achieve contraction procedures. Procedures are close to propagators for finite domain CSP. For static constraints, any set of contractors can be used, like HC4, 3B, SEED, or contractors dedicated to specific constraints. For differential constraints, we propose two main types of contractors. First, CTC VNode, a new contractor that wraps the state-of-the-art VNode audio interval solver. In fact, it's very interesting that any guaranteed ODE solver can be wrapped into a contractor that achieves domain filtering. Second, homemade ODE or integro-differential contractors. You will find some details in the paper. In practice, we use different combinations of these dynamical contractors. The last step performed by the solver is the merge of closed tubes. All pairs of solutions that intersect on all times for all dimensions are merged. This post-processing is useful when the solution trajectory is thick. In this case, it's often fruitful to first bisect the tube studied for reaching a better accuracy before merging the different subsolutions. This slide gathers the user-defined parameters required. The first one is the main precision parameter specified. It's maximum size of a solution over time. The second one is the maximum number of slices in a solution. It's an operational parameter providing a kind of trade-off between slicing and backtracking. The user must also specify the contraction strategy for differential equations. For instance, CTC VNode, followed by dyne seed guess, followed by dyne 3B. The user can also provide a set of so-called special times for a better tubes bisection and a better contraction, a more incremental contraction. For example, for the BVP with this constraint here, the special times are t equals 0 and t equals 1. A parameter is the specific slicing policy. We can split all slices or split the largest one. Another parameter is the tubes bisection policy. The tree search can bisect the largest slice or can bisect the gate occurring at one of the special times. Finally, three numerical precision parameters are detailed in the paper. To summarize, it's a significant progress to get this first generic solver, but we still need to work for reducing the number of user-defined parameters, especially those appearing in blue above. To conclude the DSCSP solver description, we give a brief overview of the related work. IVPs and interval IVPs can be handled by numerous solvers, including these ones, where VNode and CAPD are state-of-the-art. For the BVP, an incomplete numerical method exists, called shooting method, briefly described in the paper. Note that it's not an interval method. Finally, a solver designed by Cruz and Barahona, researchers from the CP community, can solve a subclass of the DACSP, and details appear in the paper too. To summarize, no existing tool uses a tree search, and we believe that no existing tool makes use of a model as simple as ours. Now present the experimental part of this work. The solver has been implemented on the top of the interval C++ library IBEX and the library dedicated to tubes and dynamical systems called TubeX and managed by the first author. The paper describes the validation on the solver on 10 systems. 4 of them appear below. First, the BVP shown in introduction. Another BVP with a nonlinear second-order ODE, it's transformed as usually into a two-dimensional first-order ODE by introducing an auxiliary variable for x dot. It's a BVP because no initial or final condition is known for x dot, and instead x is known at time 1. Third, the famous problem studied by Cruz and Barahona with a two-dimensional nonlinear ODE and an observation constraint here stating that x2 must take a value around 1.2 somewhere in the time window between 1 and 3 seconds. Finally, an interval IVP corresponding to a limit cycle, which is not easy to integrate because the solution rotates over time. On the first BVP, by using the TubeX contractor for integro-differential equations, we obtain these two solutions in about 8 seconds and 60 backtracks. The solutions have 400 slices. Solving the second BVP requires more than 80 seconds and 6 backtracks to obtain this accurate solution, made of 5,000 slices. The best differential contraction strategy for this problem is sophisticated. It calls CTCV node, followed by dyne seed guess, followed by dyne 3b. On the contrary, for the cruise problem, the contraction strategy simply amounts to a call to dyne seed guess with a large number of slices. It's solved in less than 7 seconds and only 1 backtrack. Note that the trajectory is thin for x1 and thick for x2. Finally, the limit cycle is an interval IVP where the initial condition on x1 is uncertain, but both trajectory for x1 and x2 are thick because of the rotation of the solution over time. The ODE contractor calls CTCV node and dyne basic. The solver requires about 13 seconds and 7 backtracks to obtain the solution tubes made of 1,000 slices. In conclusion, we have proposed the first version of a generic differential algebraic CSP solver. It's built on the top of a relevant model where the domains of the functional variables are tubes. It's a model implemented in the TubeX C++ library. It's based on contraction and tree search. While common in CP, tree search is new for dynamical systems. Of course, there are a lot of things to do for improving the current solver. First, we can improve its performance. One way is to use the propagation engine available now in TubeX 3 to make the contraction more incremental. Second, we will work on making the solver more automatic. We will improve the interplay between slicing and backtracking and try to remove some user-defined parameters. As seen in the experiments, in the current version, a specific differential contraction strategy is chosen for each system. It would be nice if we could identify a same strategy for a given class of systems. Finally, we can make the solver more generic in allowing the tree search to bisect indifferently tubes and basic intervals. I mean intervals of static real variables. Thanks for your attention. Do you have any questions?